make the particle vibrate beyond that. But if you think of the wave does extend all the way to plus infinity and minus infinity. The wave does go away. Although it's a very small portion that goes out, if you actually see the wave functions, but it does. So, this is a case similar to a problem that I have given you to read. Remember, the solution over here was something like that. It doesn't go to zero in this finite potential well, but then it decays exponentially to zero. It's quite comparable to, except that now my potential is not a straight one, it's half kx squared. So it keeps on increasing as x increases. Okay, so what does that mean essentially? If my particle is found beyond the classical limit. So now all my energy is constant, right? Beyond the classical limit, the potential energy is larger than my total energy. So what about my kinetic energy? Is it negative? The potential is large, greater than the total energy. So potential plus kinetic is equal to my total energy. So is the kinetic energy negative? Well, that doesn't mean anything, of course.
Bounded, you can't go away there.
Huh?
When you go to that large X, it can't be so large there.
See, the thing is, the way I have drawn it much more straight. But there is a finite probability of the wave function going out. That finite, I could have asked the same question when I was discussing tunneling. E less than B. Right? So, in this case, what is happening to the kinetic energy? Well, the answer, of course, is something more philosophical. But remember, quantum mechanics does not deal with individual events. We are always doing an ensemble measurement. So when you do an ensemble measurement, you never measure the individual energies. What you measure is, what do you measure? The average energy is equal to average of kinetic plus average of potential. So though in some cases the potential could be large, but in the other cases that potential will be small and will compensate for that large potential, the kinetic energy will never go. Okay?
But what about it's a single particle, you can't have.
Unfortunately, you don't do single particle measurements.
But if we do it for a single particle, then it would be negative.
Well, of course, kinetic energy being negative doesn't mean anything. Okay. So this is the basis of quantum mechanics, that you don't do a single particle measurement. Right? You always measure an average quantity. Right? Okay. So that's my that I would call is my classical turning point. What more is here? We know the energy levels, we know. Okay, so now of course what we've not done is still normalized it, and I'll not want you to do that calculus over here. So the normalization constant is essentially I think it's alpha by 5 to the power 1 by 4. So psi of 0 is equal to this fellow, exponent minus alpha x square by 2. Alpha we've already defined. That's my normalized form of the wave function, that's all. So that, now, what, we guess the ground state, huh? How do we guess the further excited states? Stop playing this game, huh? Let's see. The wave function of the particle in a quantum state V is given as the normalization constant, which now depends on V. In your particle in a 1D box, the normalization constant was independent of n, the quantum number. It was just square root of 2 by L. Which does give it some dimensions. HV, which is a function of something, e to the power minus y square by 2. So, let me define these. This is the normalization constant. This HV of y is known as the Hermite polynomial. Second half of the maths course will be differential equations. You'll definitely encounter Hermite polynomials. And this is the same, e to the power minus alpha x square by 2. So instead of that, I have just written y for a compact notation. So y square is equal to alpha x square, or y is equal to square root of alpha times x. Alpha, so alpha square I have defined over here as mu k by, this is the same thing which we defined above. And the normalization constant is given by 1, 2 to the power v factorial, horrible looking expressions alpha by pi to the power 1 by 4. No, I don't expect you to remember anything. All I expect you to remember is that the wave function has a normalization constant, it has got a Hermite polynomial and an exponential. So actually this exponential also, you will recognize this is something called a Gaussian function. Okay. It's a very important kind of function. Almost everything on Earth, if it distributes as a Gaussian. Some of them distribute as Lorentz series. But most of the distributions that occur, take anything, it's a natural thing. And it makes me think why everything has to distribute according to this equation. This curve is for a Gaussian distribution. So if you take the marks of a class and you take the mean, right? So the maximum number of people who get marks are at the mean position. And then everything just goes down like this. I don't know if you've studied some bit of probability, standard deviation, 5% confidence limits, 95%.